it will be communicating to the FPGA portion through the PCI Express here. Okay, right? And whatever is required for me, whatever we have compiled on a host application, I'll be telling which functions should go and get accelerated over there. That's what is required for me. Okay, so there are some questions here. So functions of XRT. See, generally what happens is when if I am going with any of the processor based designs, right? So I will have a processor and I'll have a peripheral which can be an general. If I go with the GPIOs, or if I go with an Ethernet, right? So those drivers will be automatically available. Okay, or even the Linux portion. If I'm having and Xilinx runtime libraries also, firmwares whatever is required for us, the framework what is required for us, that will be available for me uh, as a standard communicator, standard peripheral available for me on a system. Okay, whereas if it is a system, if it's a peripheral which is not a standard thing, then I need to write a drivers for that one, right? So XRT is something like runtime libraries frameworks available from Xilinx directly, which are already verified for that one. Okay, and drivers are nothing but to communicate with the peripheral. Am I clear? I think there was a question from Srijan saying that what is a function of XRT and drivers? Okay, right. Right. I think already I have answered these questions from Vaishnavi also. Right. So any questions are there apart from this? Okay. Right. If it is an edge device, edge means, for example, if it is something like which we are having a Zinc UltraScale plus MPSoC devices, or Zinc 7000 devices are available, right? Where our processor will be there, okay, and I will have the PL fabric also available, okay. So all the application whatever is required for me, it will be written here, okay, and we'll have this XRT available for this, okay, and kernels, the functions what is required, it will be written, okay. I'll be telling it very clearly which portion of my code should go and sit onto, whether to it should be on fabric side, PL side, or it should be onto if it is a virtual devices, it can go to the A engines or DSP engines very properly. That's also required for us. Okay, right, right. So to access that, to kind of when you're moving when there is a data movement happening from PS to PL kind of thing, right? Then we require to have some sort of memories also, right? It can be an internal memory or it can be an external memory, right? So that can be made it available for the PS-PL communications on the chip product. Okay, right,
ఆల్రెడీ వినుంటారు కదా, మళ్ళీ చెప్పాలా?
right. So our most of our
వద్దు, వదిలేసేయండి.
edge cloud-based things, whatever is happening, it will be based on PCI Express interface, right? So our host program will be compiled on the host CPU, okay? Then the global
తర్వాత ఏం
memories,
జరుగుతుంది?
then the
నేను
kernels
మెసేజ్
will be there.
పెట్టుకోవాలి.
Kernels are nothing but our applications, whichever is required for me to go for
అది ఎవరు
accelerations.
చెప్తారు?
Okay,
నేను అనేది మీరు ఇప్పుడు పిలిచి అడిగాను, మీరు వచ్చారు కాబట్టి అడగట్లేదు. No, what kind
right?
of communication you are doing?
So our
What you say?
applications,
నేను చెప్పింది నా ఉద్దేశం.
whatever we are trying to put, right? So it will be accessing the global memories, like accessible to host processor and kernels completely.
దేంటిది?
Host memory only accessible by the host applications completely. Am I clear?
ఏమైనా అటెండ్ అవుతున్నారా మీరు? ఇప్పుడు దీంట్లో ఏముంది?
Right.
అటెండ్ అవుతున్నారా?
So this is how the data transfer will happen. Okay. So host data transfer
అది కూడా చూడలే.
through
ఒకసారి
global memory.
రాసి
Kernel uses that data. Okay. And again, host transfer results into host memory completely for us. The whole sections
ఏం
can
తెలియదు
be
అసలు వచ్చారు సంతకం. నేను
relinked
అంతే
very
కదా ఉంది.
properly for that.
మీరు ఏదైనా ఉంటే
Okay.
ఆదివారం ఫోన్ చేస్తారు, నేను అందరికి మెసేజ్ పెట్టుకొని అడగతా.
Sujan, I told you initially also what is this XRT and drivers required for. Again, same question is repeating.
అసలు అది ఏంటో కూడా నేను చూడలేదు. వచ్చి ఇప్పుడు మిగతా
Right.
ట్రైనింగ్ గురించి కరెక్టే. మీరు వచ్చినప్పుడు డిసైడ్ అయ్యి వచ్చారు, అంతే కదా? ఏదో రాసుకుని వచ్చి ఉంటారు. నా పని ఏంటి?
See, there is a question. I don't know. IIIT Bhubaneswar is the name given here. Okay. Can I write code for PCI interface, or it's already available? See, PCI interface is already this when we insert the card, right? So what happens is the the XRTs
SI
will be
పోస్టులకి
installed
వెళ్ళాను
and
కదా.
other things will be whatever is required for us, it will be enabled. Okay, not required for us to go for a communication based writing code here. Okay, see for example, if I'm starting as a developer, if I'm an hardware and software engineer where I'm trying to do a
ఫైనల్గా
communication
క్లియర్గా
between
మీరు
PCI Express,
చెప్పాలనుకున్నది చెప్పండి.
that
అది
will take like requires to write PCI
డిజిటల్
IP
కమ్యూనికేషన్
code,
జెన్యూన్
then
చెక్
write
చేసి
the host memory code, all these things, whatever is required for
అక్కడికి
me,
అలాగే
that
ఉంటుంది.
will go
నా
off.
వర్షన్ అలాగే ఉంటుంది.
Okay.
ఎంత తిట్టుకున్నా సరే అది డీసీ అర్థమైతే కానీ అర్థం కాదు. నేను అన్నది అర్థమైంది కదా మీకు. వేరే వాళ్ళు చెప్పారు నేను వద్దు ఇంకొకటి కూడా చూసుకోమని చెప్తున్నా, వద్దు అని చెప్పట్లేదు. దెర్ కుడ్ బి అ రీజన్.
రైట్.
ఇప్పుడు మెంటరింగ్ అంటే ఇంకా అక్కడ వరకు వస్తుంది అన్న, ఏదో ఒక్కరోజు వచ్చి సంతకం వరకు కాదు. ఏంటి
ఓకే,
నేను అసలు ఏం చదవలేదు ఇప్పుడు కూడా. మీరు పై పైన చూస్తాను కానీ అసలు నాకు
I think it's clear.
అందరికి ఇచ్చి ఏమన్నారు ఇది నాకు ఇష్టం లేదంటే ఏం చేయాలి?
See, host memory is something which it's available as in the server,
వెళ్ళి అడగండి,
rack
నాకు
server.
ఇష్టం లేదు నెక్స్ట్
Okay.
వరకు ఉండను అంటే ఏం చేయాలి? మెంటర్ అడగమన్నారు అని అడగండి. నీకు ఇష్టం ఉందా? ఇప్పుడు ఓపెన్గా అడిగేస్తాయి నాకు ఇంకా బ్యాక్ ఉందని చెప్పి.
See here, host memory is our CPU, the rack server, whatever we are having it, right? They will have their own memories. It can be an DDR memory, it can be an QDR memories, or whatever the memories, whatever is required for me on the rack server, that will be available. Okay, my global memory is what is available on the FPG card. Am I clear?
అదేనమ్మా చెప్పేది. ఇది ఎవరైతే ఇచ్చారో నాకు ఏది ఇంట్రెస్ట్ లేదు, ఇలా ఉంది, నేను ఎన్పిటిఎల్లోనే అది
right. So when we are doing an acceleration, right, so we try to go with very two things. One is pipelining and another one is parallelism. Okay, let us go with that one. Okay, so what is pipelining?
అది నువ్వు నాకు చెప్పగలగాలి, నేను నీకు కాదు చెప్పేది. ఓకేనా?
Right, so it will have multiple stages of pipelining. Okay, right. So computational structures, one computation per clock, right? So results will be passed on to next computational stage, and each stage loads simultaneously, right? All these things will be taken care, right? So if I take an example of what we are doing here, okay, so there is a square plus 1 into 3 we are doing it, okay, right? So pipelining stage 1, the input is first value is 3 is coming there, okay, right? So 3 is coming here, so 3 squared is 9, okay, but plus 1 will not be computated because this one is not available to us, okay, right? So whereas in the next pipeline stage 2, this 5 will come, this becomes 25, but whereas here this becomes 10, okay, this is still not executed. This will execute only in the third clock cycle, okay. In third, 7 will be coming 49, here it will become 26, and here it will become 30 because 10 into 3 is 30, right? So here we are not using any of the memory access here, okay. Am I clear? Any questions are there? Any questions? Right? The pipelines or the computational structures where a single piece of computation is performed in a clock cycle. The result of that portion.
Processor, third one.
Sorry, I'm not able to hear you.
Explain the processor pipelining. Sir, actually what happened, third process when it will be plus. So second clock cycle, then after third. So please sir explain again this one.
See, in the first input is our 3.
Yes sir.
So first it comes to this. Sorry. So first 3 will come. Okay. The first clock cycle, 3 square will be executed. Okay.
Okay sir.
Right. Then this will not get executed because it's not come to the second clock yet. So my second input will come here. So at that time, this second, at next clock cycle, this will get added. So it was earlier 9 was there, so this becomes 10. So this value. See, first this is square, and this is plus 1, and this is into 3.
Okay, sir.
Okay. Right. It should see if it is an loop which is required to run for some more clock cycles, I can put it like that, not a problem. Okay, right? So pipelines are the computational structures where a single piece of computation is performed in a clock cycle for us, right? The result of that portion is passed to the next pipeline stage, where the next portion of the computation is performed. Okay, right? So the benefit of this structure is that when the second pipeline stage is being loaded with the result of the first stage, the first stage is being loaded with the new piece of information there, right? Right? Am I clear?
Yes, sir.
Right. So since result is produced by each stage on each clock, the end of the second clock period sees both the first and second stages passing the result to the subsequent stages. Right. So this example, whatever we have shown to you, is a 3-stage pipeline. Until the pipeline fills after the third clock cycle, the outputs are invalid. However, after this third clock cycle, the pipeline produces a result every clock cycle, right? So I'll get my output on every clock cycles afterwards. Am I clear? So up to this third clock cycles, there will be latency of 3 clock cycles. Okay. Sometimes pipeline helps us a lot in some of the tasks, right? So if it is not, pipelining is not there, means what has to happen? First, it has to load the data, right? Am I clear or not? Then fetch the data, store it somewhere, perform the tasks, and again store back to the memory or somewhere else, and then go back to the task. So it requires some almost like 4 to 5 clock cycles are required for one particular operations. Am I clear?
Yes, sir.
Okay. Right. So I was seeing some questions here. Okay. Yeah, I think I've already answered some of the questions. What are the methods generally followed to avoid pipeline hazards? So generally, we try to use some registers so that it will not be a problem for us. Okay, right? Okay, right. Any questions are there? Right. So when is the pipeline will be beneficial for us? Like for example, if I take an example of pi n, okay, n is the number of datum to process, and that pipeline once is filled is producing output at the clock rate. Okay, right? Right. So if I take an example like this, right? So you think that there is an overhead for implementing a kernel, right? It requires an area of queuing data, right? In the case of pipeline accelerator, filling the pipe, how much data needs to be processing before it makes sense to go through the effort of implementing the kernel, right? So we'll just try to understand what is learned from the Amdahl's law. Okay? If the performance lag is due to only a small portion of the code, then even an infinite acceleration will not be helpful for us, right? Are you getting me? If the performance lag is due to only a small portion of the code, then even an infinite acceleration will not help us for us. Okay, right? So assuming that our system performance goals, let's quickly consider the type of speed up what we require to see up right here. Okay, knowing that the processing performance is linear for CPUs and there are n number of datum to process, and that pipeline once filled is producing an output at the clock for us. Okay, so our rough performance, whatever we are trying to put, is about by a factor of pi. Okay, right? So we can proceed to a slightly more realistic acceleration equation that considers how much data must be transferred here. Okay, that is the depth of pipe what is required and the number of datum required for this processing. Right. So let's consider our simple 3-element pipe. Okay. So assume that it takes 100 clock cycles to set up the data, right? So this might be moving the data from the processor memory to the cache that feeds into the pipe, or maybe it's the command to the DMA that loads the data from DDR memory, right? So with this configuration, how much data is required for processing before we reach the break-even point? Okay, you know that the processor, whatever we are trying to take it, right, requires 5 into n clock cycles to process the data, whereas the pipeline requires 100 cycles for setup. Okay, 100 more cycles to return the data, so 3 cycles to fill the queue, and then n more cycles to process the data for us. Okay, so from our equation, whatever we got it, right, so at least 41 pieces of data need processing before the benefit of pipeline kernel is realized for us. This means that there is a clear advantage of streaming data or frame data with a payload greater than 41 data in size. Okay, right? Right. Once the data set becomes larger, however, we see pipelining easily beating the CPU. For example, using our previous assumptions, if there are 1,000 pieces of data is there, then the CPU will take 5,000 clock cycles, while pipelining will take only the 1,000 fly clocks for us. It's almost like a 5:1 ratio for us. Right? The deeper the computational process and more data requires processing, the greater the gains by using the pipeline architecture. Am I clear? Any questions? Okay. Right. Any questions are there? Right. So n is the number of datum to process, and that the pipeline once is filled is producing output at the clock rate. Okay. Am I clear? DDR memory is double data rate memory. Okay. So it's a formula given by Amdahl. Amdahl's law we call it as. Okay. So based on that, we have come up to the advantage function. I think I am not required to go for too much technical of what that law tells and all. Is it clear? Yes. Right. Right. So how much is the pipeline cycles? Total CPU cycles. Okay. Right. So parallelism. Right. So parallelism is nothing but simultaneous operations, what we call it as, right? So parallel architectures are structures where more than one operation is occurring simultaneously. Okay. So consider each process or a thread as a distinct operation. Okay, a process could be a single operation, or it might be a pipeline operation. See, parallel architecture will have process or thread that each process can be pipeline. Am I clear? Okay, right? A process what we are using, it can be a single operation, or it can be a pipeline operation, or even another parallel architecture also. That's also is possible, right? So it is very important to make like distinct between parallelism in hardware versus software implementations, right? So when we are dealing with software, one needs to be very clear like how many cores are available, right? So that will be required for us to understand can we go for parallelism there or not. Okay, right? In a single core system, parallelism, whatever we are trying, it will be like mimicked by offering different time slices to each thread, so that there is an illusion of simultaneity, but that the reality is not that way. Okay, so there are certainly benefits to this approach, but there are many drawbacks as well, including significant performance hits. 1 minute. 1 minute, 1 minute. Right? The drawbacks is like performance hits due to the having switch contexts, right? Where there are systems that support multiple cores, true simultaneity can be achieved, but at the cost of requiring some type of core. That's management system, we call it as, okay? So it will be provided by an operating system, or it can be from a hypervisor, okay? Right? So this overhead will diminish the overall system performance here. Whereas in hardware implementations, almost always run truly simultaneously, as there is no intrinsic of overhead once the fabric is configured. To be fair, we are omitting a discussion about thread synchronizations, which must occur in both hardware and software designs. This synchronization is required for whatever management mechanism is in place and needs to know when a thread is complete so that it can manage data transfer to an action. I hope it's clear. Any questions are there? I hope my screen is visible.
Yes, sir. Your screen is visible.
Right. Thank you. Okay. So hardware applications boosting application performance. Okay. So initially we see that the functions 1 through 5 are implemented in software. Okay. Right. And these functions are executed sequentially. Right. The size of each function block represents the amount of time required for the function to complete. Function 2 will take more time. Okay. Using hardware acceleration, computational intensive functions can not only execute faster in hardware, but they can be executed in parallel also, right? So depending on the algorithm being implemented, note that some functions are best in software, including whatever is required to handle communication and basic housekeeping, all these things. Okay. Here the decision is to make was to made leave function 1 and 5 running in the CPU and move function 2, 3, 4 to the hardware. That's what is required for us. Okay, right? There are two hardware-centric concepts here. One is pipelining and another one is parallelism. Okay, so pipelining is the process of performing a portion of the overall computation at each clock cycles and passing the result to the whatever we got it to the next stage. Okay, right? So this technique is good if the pipe is once the pipe is filled. Okay, it will provide a result on each clock cycles after that, right? Right. So in this example, function 1 will be running on the CPU, function 2 and function 3 execute in parallel in hardware, right? And the output of function 3 goes to the function 4. Okay. 1 minute. Right. Then function 5 is executed in the CPU again for us. Am I clear? Any doubts till now? Are you getting me? What I am trying to let you know about this? Right. So here there are 5 functions. Okay. So function 1 and function 5 will be executing on the CPU. Okay, whereas function 2, 3, 4 will be on the acceleration on the FPGA fabric, what we call it as. Okay, am I clear? The output of function 3 goes to function 4, then function 4 to function 5 it will go. Okay, right? So now the question is very clear, like what handles this acceleration? The fabric, the dedicated silicon resources handles the computational intensive, deeply pipelined, massively parallel operations. The CPU handles the rest for us. Okay, our device will have many advantages over traditional CPU or GPU acceleration, including implementing any functions that can run a processor, resulting in a better performance at lower dissipation, power dissipations, and all those things. Okay. Okay, there is a question from Anita. Doesn't function 3 need the output from function 3? I couldn't I think the question is wrong, Anita. There is no such kind of thing. Function 1 gives the result to function 2 and function 3 both, and function 3 is giving output to function 4, and then function 4 is giving the output to function 5, and 2 is also going to 5. Okay. Am I clear? Right. Just to show an example to you, okay? So it can be multiple functions also. There is no risk, right? But think that if the output of one function is required by the next function, then you have to wait for that function to complete. Again, what is the point of acceleration there? Right? What we try to do is we try to make it like if you have an array, right? We split that array to multiple registers so that it can do a faster work for us. That's kind of example I can give it to you. Okay. Am I clear? Any doubts to me till now? Any questions are there? Any questions are there? So can you think that independent ones are that can be? I couldn't understand the questions, Dolananda. Yeah, we have a demo. Don't worry about that. I'm just trying to give you a glimpse of what is this Vitess software is about. Am I clear? Right? Okay. Right. So when you are going with acceleration, right? So we need to tell the tool, okay, which one will be on the software, which will be on the acceleration. That is very important for us, right? So we know very well now accelerating a program requires the splitting of applications between host application and hardware accelerated kernels, right? With a communication channel between them. It can be an AXI, it can be an PCI Express. I don't mind for that one. Am I clear? Right? So the build process follows a standard compilation and linking process for both the host, right? Build the host program and the FPGA binary, first things. Okay, let's go by build the host program, right? So the host program will be written in C or C++ using an OpenCL APIs. Okay, right? So it will be compiled using GNU C++ compiler or G++, right? Or the GNU C++ ARM cross compiler, what is required for us, right? Which will be based on our devices, right? Or whatever we are trying to do. If you are using the Zinc, right? So it will be an cross compiler G++, GNU C++ ARM cross compiler will be utilized in these cases. Okay, or if it is a host compiler completely, it will be a GNU C++ compiler. Okay, right? So each source file is compiled to an object file .o and linked with the Xilinx runtime shared library to create the executable that runs on the host CPU. Okay, if it is a software application. Am I clear? Am I clear to you?
Yes, sir. Yes, sir.
Sir, what will be there in XRT?
XRT, it's a framework, sir. Xilinx runtime libraries and frameworks will be there. See, for example, if I'm trying to compile a code which is required to be given to an Alveo card, right? So what happens is I need to compile that code with respect to what is available on my hardware devices. Only the drivers will not be able to help us because there again PCI Express transactions has to happen. So that kind of things has to be taken care by these XRT things.
There
If
is
it is
something
an
like hardware
if it is an
specific libraries you will be linking.
exactly.
Okay.
It will be similar to our drivers, what we call it as. Similar to our drivers. Okay. Apart from drivers, what happens is it can be it will be in a C or C++ code, whereas in framework, what we call it as is we'll have more of realistic drivers required for us. For example, if it is required to be for OS specific, or it should be required to some sort of bare metal application. So these things has to be compiled very properly. Am I clear?
Yes, sir.
Okay. So Kriya KV260 also, yes, it can be used, but there are some limitations in that one because it has got uh, DPU involved in that cases. So be careful while using it. That's all. Okay. Ramu, there was a question from you.
పిచ్చి కావాలా
Right.
మళ్ళీ వాళ్ళు చెప్తారు పిల్లల కింద
Right.
కూర్చుంటారు
So am I clear? No doubt. Can I move further? So this is about how the fast program will be built. Right. I'll be writing a C++ code that will be compiled to an object file .o file. Okay. And it will be linked with the shared library, and then it will be creating a host executable what is required for us. Okay. Right. So once my hosting is completed, now my FPGA kernels will come into picture, right? So I'll write C, C++. See, FPGA kernel can be anything. It can be a C code, it can be a C++ code, or it can even be an RTL code for us, right? So, but we have to compile it with the help of VTIS compiler, V++ compiler, what we call it as. Okay, right? So this VTIS compiler compiles the kernel code into a Xilinx object file, and then it will link to the XO files into the FPGA binary called as .xcl bin. Okay, so here it will be our .xcl bin. Generally, for acceleration point of things, we try to use more of the Versal VCK 190 board or VCK 5000 accelerator cards or Alveo cards, whatever is required, U55C or U200C or all these things cards are there. So that will be giving you a .xcl bin. So our VTIS environment will give us that .xcl bin file required for us. Okay. See, when this there was a question from a lot of people earlier also that okay, when this xcl bin will not be created. See, if your code is not compiled properly, it is not linked properly, obviously it will give a error to you. So you should have a look on that one. Then obviously it will give a proper output for us. Okay. So these are these things which you should be always remembering here. Okay. So it's not like okay. There was a question. There was a message from Mohammed saying that can we call XRT as translators? No, it's not a translator, my dear friend. It's like a framework what we call it as. Okay, right?
Sir, these FPGA binaries are bitstream files.
It will be a bitstream file. This see most of the new devices which are available like Versal and Alveo cards which are available, right? So there will be a .xcl bin files. Bin files will be there. It will be like binary files only. Okay. Right. So Hemant, she had asked me that the default GCC compiler are installed in VTIS or not. See, what happens is, uh, this VTIS tool, whatever we are having it, it has got GCC compiler will be available, but we are targeting it to our specific XR the FPGA boards, right? For example, if I go with Zinc UltraScale plus MPSoC, or if I go with Zinc 7000, right? So I need to have C compiler plus cross compiler. Both are required for us. That's what I'm trying to tell you. Okay.
Sir, here when you say C, C++, you'll be using a HLS kind of thing, or you call it as a VTIS compiler?
See, HLS is a basic building block tool which came to our mind, and with the HLS tool we can go for acceleration, but it will be functional based. I can take one particular function at one time. Whereas in VTIS, I can take multiple functions and different engines I can put. I can put it in some portion in FPGA, some portions in PS, some portions in AI engines that I can take it. I can uh, um, dividing of the two application code here. Am I clear?
Sir, do you mean to say that you will be having functions maybe implemented in C or C++, and you will be having the
Sir,
flexibility to put it
Ravi
on?
Kumar sir,
Yes, sir.
Ravi Kumar sir, just wanted to tell you, HLS was the tool first which came. Okay, that tool only is based for used for acceleration point of things. Whereas earlier, what happened was when we go for a HLS tool, there I have to select the application code which is running already, which is already pre running on some processor. Okay, so that processor, if it is taking more clock cycles, I can take one particular function at one time, and I can tell the tool that okay, this function I want to go for converting it to RTL so that it becomes faster. Okay, am I clear?
Yes, sir. Yes, sir.
Whereas
Clear,
in
sir.
Vitis acceleration, I can choose multiple functions. Tell that not only in FPGAs, some portion in PS, some portion in adaptable engines, some portion in FPGAs. That I can tell it. I can divide like that way.
Okay, sir.
Am I clear now?
Okay, sir. Clear. Clear.
Okay. So there is a question from Praveen. Whatever the bitstreams files are generated by the tool is generally I don't know .sof extension, my dear friends. It will be .xcl bin here in our cases. Okay. Okay. There is one more question from Hemant saying that libraries we use in the kernel code defaultly installed, or we install that. See, most of the codes, whatever you are writing, some libraries we create it. For example, if I'm creating my own custom host code, I'm writing it, right? So I wanted to use my own um, uh, uh, the data spectrum, what we call it as, right? So that I wanted to use it on my own thing. Okay, I can use my custom specifications very properly in that header files and all those things. Whereas by default, some other libraries or whichever is required, it will be available because we'll be using most of the times OpenCL kernels. OpenCL kernel is available freely. Okay, am I clear? Right. So Naveen, we will be writing all our C or C++ code in Vitis completely. Right. So compiler, see, when I'll give you an example. See, when you write your code, C code or C++ code in your normal Ubuntu machines, right? So I'll be compiling it with help of GCC compiler, which is already predefined in our Linux or in the Windows. If you're going to go with Windows, then I have to install that Borland C or some other compiler required for that to compile it. Okay, right? So whereas here Vitis, what is it is doing is it's taking care of all my compilations required for me, and it's giving me a result. Okay, right? XO is our object files, Srijan. Right? Because in our CPU, what happens is I'll compile the code, I'll generate the object files, and then object files will be converted to executable files. Same way here also, we'll be writing a C or C++ code, then we'll compile it. The compiler will compile the kernel code into a Xilinx object file, okay, and then it will be linked with the .xo files for it to create the FPGA files. Okay, it's object file only. Vitis means Vitis ID, yes. Okay. So there is a question that does Vitis compiler take care which functions to be executed? So it will not take care automatically by itself. You has to decide it. Okay. It is you who has to decide it. Am I clear? Right. Right. So we have seen in the previous things like what is which can be split into software, hardware, all these things. Okay, there is still some questions coming. Okay, Anita, it depends. See, generally, okay, Praveen, I think I already answered your .xo questions directly. Anita is asking like usually how can we decide what to do, what to put on PS and PL, sir? See, it depends on. See, for example, I was showing you an example in the previous slides and all. There I was showing some five functions with it. Function 1, 2, 3, 4, 5. Okay, so these 5 functions, I wanted to tell the tool that okay, function 1 and function 5 will be running on CPU, that's on PS, whereas function 2, 3, 4 will be running on a PL. That I have decided because function 2 was taking more clock cycles to implement to work on a processor, right? So based on that only, that reason only, I'll be able to choose which one is on PS, which one is on PM. Am I clear? Right. So we have seen a lot of things discussing about how a system is split into software and hardware components. Okay, and now let us see how our uh, tool makes it possible to make that environment very problem. That is Vitis development environment, right? So Vitis, it's a unified software platform. It's a tool that combines all aspect of AMD software development into a single overarching environment for us. Okay, the Vitis software platform supports both types of primary users: those who want to wish to perform traditional embedded software development, as well as those who want to go for accelerating the applications, right? The traditional developers benefit from use of there'll be a lot of development and deployment of embedded applications, tool chains required, programming tools and debuggers, emulators, all these things are there for us. Okay, and for people who are interested to go with application acceleration, right? So they can go with these tools also supported, including specialized libraries, support of IPs, everything will be available for us. Okay, right? So it will be a same platform for different personals who are trying to utilize here. Okay, so if somebody is working on Zinc 7000, somebody is working on Kriya, somebody is working on Zinc Ultra Scale Plus, Versal device cards, Verium cards, Alveo cards, what we call it as, right? So all these things will be taken care by this with this things. Okay, so Srijan sir, I was telling you very properly. See, our compiler V++ compiler, internally it is calling HLS only there. That's why I'm trying to tell you. See, it's a basic building block. I'll select the functions. If I'm selecting function 2 and 3 in my code, saying that this 2, 3, 4 should go into a PL side, internally it is calling the HLS tool to create that as IP and attach to the processor immediately. It's not required for me to usually make it manually by myself here. Okay, am I clear? Right. So I'll have RTL kernel wizard, AI engine compiler. So AI engine will come into picture only in the virtual devices. Okay, right. So it can be on edge or cloud applications very properly. Any doubts? Any doubts are there till now? Okay, any doubts till now? Okay, let's break for 5 minutes. Let's have a break because we'll just have water and come. That's the reason, right? So, okay. So there is one question from Sai Sri: is